Hello everyone, this is Ankit Shivare. In the earlier modules, we discussed on intrinsic semiconductor, extrinsic semiconductor. In this module, we are going to talk on the energy band distribution in the semiconductor. Okay. Also, we are going to see how the electrons and holes distribute in the semiconductor and how can we quantify them. So, in this electron distribution, we are going to talk a term called as fermi dirac distribution. So it is a function which gives the probability that an available energy state at E will be occupied by an electron at absolute temperature T. So this was developed by following principles of wave nature of electrons and Pauli's exclusion principle. So look, we are not going on to the experimental results that how these terms are coming. We are going to accept the results as it is by the scientist community. Okay. So what is the fermi dirac distribution function? That Fe is given by 1 plus exponential E minus Ef by kT. So what this is showing you that the probability of finding electron at energy state E is given by 1 plus exponential E minus Ef by kT. Okay. So what Ef is nothing but the Fermi level energy. What it shows you, suppose I want to find out the probability of finding an electron at energy state Ef. So F at E is equal to Ef is given by 1 plus exponential Ef minus Ef by kT. So exponential 0 is nothing but what? 1. So this is 1 by 2. So probability of finding electron at energy state E is equal to Ef is nothing but half. Okay. Where K is Boltzmann constant. Also value of this is 8.62 into 10 to the minus 5 electron volt per Kelvin. So this is the unit that we are going to use. There is one more unit, but it is not required for our case, because generally energy we are going to write in terms of electron volts, joule per Kelvin. So let us see in details how the plot of Fe, that is what, 1 plus exponential E minus Ef whole by kT looks like. So when you see the plot of Fe with respect to energy E, it looks in this manner. This is at T is equal to 0 Kelvin. Now you can see when, and this is E is equal to Ef. Okay. So at T is equal to 0 Kelvin, what we see, when E is less than Ef, so this is 0. So exponential 1 by exponential something divided by 0. Okay. So this term will go to infinity or minus infinity. Okay. So when E is less than Ef, so E is less than Ef, so this is exponential minus infinity. So this is what? This is almost 0. So the F probability is 1. Fe is 1. And when E is greater than Ef, so this term exponential infinity, so this is infinity, denominator is infinity, 1 by infinity is 0. So Fe is nothing but 0. So this plot is showing you the same case. Okay. So this is 1 and this is 0. So what is showing you that the entire energy states below Ef are occupied by electrons and energy state above Ef are vacant. Okay. So all the electrons below energy state Ef are occupied. All the electrons above, all the energy states above Ef are vacant. So it is showing you that all energy states below E less than Ef are occupied. Okay. And what this is showing you, that all the energy states above Ef are. So this is the Fermi Dirac distribution function that is coming to you. Now as temperature increases and you do mathematical calculations in your calculator, what you will see, this type of plot. So suppose this is at temperature T2. So when T2 is greater than, here T2 will be greater than T1. Okay. So this is the plot Fermi Dirac distribution function will look to you. Okay. Now one more thing you see, that the Fermi Dirac distribution function is symmetrical about Ef. Okay. So it is the symmetrical point. So what I mean to say that F of E plus delta E is nothing but equal to 1 minus F of E minus delta E. So what it is saying, that the value of probability of finding electron above energy state E by delta E terms will be equivalent to the vacant state, that is below E. Okay, so that is same. Okay, so Fermi's function is symmetrical above EF for all temperature, about EF for all temperature. Okay, so probability that state delta E above EF is filled is equal to the probability of state delta E below EF is empty. Okay, what is Fe? Fe is nothing but probability of occupancy of an available state at energy E. Okay, so one question that will arise, we know the band diagram for silicon, how it looks like. This is your EC, this is your EV. So in energy band diagram for silicon, we know that the energy gap, that Eg is what? 1.1 electron volt. Okay, so this is the band gap energy, and we also know that the intrinsic carrier concentration is also equal to the whole concentration. Okay, so that is almost 1.5 into 10 to the power of 10 per centimeter cube for silicon. So in this case, the Fermi level is almost in between the EC and EV. This is the case for silicon. Now what happens if we dope with this silicon with donor ion impurities? Okay, so how the band gap diagram will look? Okay, in that case, suppose we doped this silicon with group 5 elements. So what this is called as N-type semiconductor. How will the energy band diagram looks? So this is your EC, this is your EV. Now the electrons will be more towards the conduction band, because number of electrons that are available at conduction band will be more. So actually the introduction of N-type impurities or donor type impurities will create one more energy level, that is E donor, okay, which is very close to EC. Okay, so suppose you apply at room temperature, that is suppose you apply even 300 Kelvin, that is room temperature, the electrons which are available in this band will jump immediately to the conduction band level, and these electrons are now freely available for conduction. So most of the electrons at room temperature will go to the conduction band, and when they are in the conduction band, so they can conduct for electricity. Okay, the Fermi energy level also, that EF will be also near to this EC, because the finding of probability of electrons at near energy state EC will be more. Okay, so the Fe, that is EF level, that is a electron level, that is EF, will be more towards the EC. Similarly, for group 3 elements, if suppose they combined with group 3 elements, so how it looks? So this is your EC, this is your EV, and this is the acceptor IR impurity. So the introduction of group 3 elements into the semiconductor, what will it do? It will have holes. So at room temperature, what happens? Suppose at 300 Kelvin, these holes will go to the valence band and they will be available for conduction. Okay, and this is your Fermi energy level, that is EF. So Fermi energy level will be close towards the EV. Okay, so what this EF will signify? The probability of finding an hole. Okay, so more number of electrons are available near this valence band, which can conduct actually. So I told you this bubble analogy. Okay, actually the water is moving. Okay, it looks like the air bubble is moving up, but actually the water is filling that bubble. Okay, similarly is for the holes. Okay, now let us see how this Fermi energy level can be used mathematically to compute the electron density or number of electrons. Okay, so we know this picture, that suppose this is my energy level E, and let us plot Fe along with this. Earlier the plot was what? Earlier the Fe was above and E was below, and this was the plot that we were plotting. Okay, and this was your EF level. Okay. Now we have just rotated the axis, E here and Fe here. Now when you see, this plot will look like this. Okay. So what this plot is showing you for intrinsic semiconductor. So for intrinsic semiconductor, what will be the case? That this is your E F I. This is the intrinsic semiconductor. Okay. We also know that the conduction band is here for this case, EC here, and EV will be at this energy level. Okay, this is your EV, and this is your Fermi energy level, EFI. Okay, or EI we can say directly. Okay, so the probability of finding electron at EFI will be what? So probability of finding electron at energy level EI is nothing but 1 by 2. Okay, this is for intrinsic semiconductor. So if suppose we want to see the electron concentration will be equal. Okay, so the electron concentration will be equal to the hole concentration. So Ni will be equal to Pi. Okay. Now suppose we see for the extrinsic semiconductor and we plot. So this is Fe with respect to E, and this is for extrinsic semiconductor. So what we see, that this is the Fermi level plot. For N type, this will look like this. Okay, so you can see this EF is more towards the EC. So the probability of finding electron at energy level EF is what? 1 by 2. We know this thing. Okay, so this is your N type semiconductor. Okay, for P type, how the diagram looks like. So this was your E and this is your Fe. Similarly, this is your Fe and this is your E. Okay, so for N type it will look like this. So EF will be close towards the EV. Okay, so this is your Fe versus E. Okay, so you can see that EF is very close towards the valence band. Okay, so almost all the holes are available here. So this is your Fe versus E plot for P type, Fe versus E plot for N type. Okay, so we also know that the electron concentration is nothing but N naught. Suppose we want to calculate the electron concentration, it will be what? From EC to infinity. What is EC? EC is here, and above EC there is the electrons. Okay, we know that between EC and EV there are no electrons. Okay, because this is the band gap energy, that is Eg. So in this, the probability of finding electron at Eg is what? 0. Okay, means according to the Fermi distribution function there is some probability, but actually we know that in the band gap energy there are no energy states. If suppose there are no energy states, it means no electrons can exist. Okay, so if suppose no electrons can exist, then the electrons can exist from EC to the infinity level, and from EV to the infinity level holes can exist. Okay, so EC to infinity, the electron concentration will be there. So this is given by Fe into Ne. So that is probability of finding electron multiplied by energy states that are available by dE integration. Okay, so this is what this is showing you, density of states per centimeter cube in the energy range dE. So one more thing we should remember, that energy states, when you see the value, this is proportional to the e to the power of 1 by 2. But we know that Fe, it decreases as E increases, because Fe is given by what? 1 by 1 plus exponential E minus Ef by kT. So you can see this E term, as E increases, so this term will go towards 0. Okay, so Fe will go towards 0. So Fe into Ne will go towards 0. Okay, because it is exponentially decreasing. Okay, so this value will go to 0 very quickly. Okay, so most of the electrons, means at E is equal to Ec, so Fec is what? The probability of finding an electron at energy state Ec is what? 1 by 1 plus exponential Ec minus Ef by kT. We have just replaced this E by Ec. Okay, nothing more than that. Okay, and also we are assuming that Ec minus Ef is much greater than kT. So what we are assuming, that Ec minus Ef is much greater than kT. Look, kT is very small value, right? It is 0.026 electron volt. So at least we are assuming that the energy states, that the difference between EC and EF is much greater than kT, at least 5 to 10 times more. Okay, so 0.26 electron volt will be normally there. Okay, so at room temperature this much energy is available, that's why the electrons are liberated towards the conduction band. Okay, so if this is the case, so we can see this F at E is equal to EC is nothing but what? 1 by 1 plus exponential EC minus EF by kT, and we can also write in as this is nothing but exponential minus of EC minus EF by kT. Why this is coming? Because we have assumed that EC minus EF is much greater than kT, so this entire term will be much greater than 1, so we can write down in this manner. So therefore, for this case N naught will be given by what? NC exponential minus of EC minus EF by kT. So now you can see for N-type semiconductor, this is the conduction band level, this is the Fermi level that you are getting, and this is the valence band level, and this is EG, that is band gap energy. Okay, so you can now determine the electron concentration by seeing this difference, the difference between the energy states. Okay, and this is what? This is effective density of states. Why this is coming up? Because we know most of the electrons that are available will be in the energy state of EC, because as you go above EC level, this value will decrease rapidly and this probability of finding electron will go towards 0. So most of the electrons are available at this energy state EC. So we are only worried about the density of states at the conduction band. Okay, so we are just seeing the density of states at conduction band H. So this is also referred to as effective density of states. Okay, I hope you are clear with the terms. Okay, where this effective density of states, that mathematically this NC value is given by 2 pi Mn star kT by H square to the power of 3 by 2, where Mn star is nothing but the effective mass. So this is the effective density of states equation. Similarly, you can determine and write down equation for the concentration of holes, that is P naught, is given by NV exponential minus EF minus EV divided by kT, where NV is nothing but equal to 2 times 2 pi MP star, that is effective mass of holes, kT divided by H square to the power of 3 by 2. So don't confuse with these lengthy equations. I will tell you in the problems how to solve these type of questions. Okay. Thank you. We will meet in the next module.